Okay, Physics 30. So to start our day off, we are going to do a comprehension check. So I am going to get you to pause the video here. I want you to try out these questions. When you're done, you're going to play the video and we're going to come and check your answers. Obviously, I'm not there and I can't give you your rating, but again, you will know kind of where you're at. Okay, so pause the video here. Okay, so an object with a positive charge is used to charge a neutral object by induction. So what kind of charge will the neutral object have after charging? Use a diagram to explain this process. Okay, so I'm going to have my own diagram. Again, you can have your own. I'm going to pretend that I have, so this is one. I want to make that just thicker, sorry. Okay, so this is 1. I want to have a positively charged object. I'm going to have my baguette looking rod here. Okay, and then I'm going to say that I have my neutral object, so it's going to have a bunch of positives and negatives around. Perfect. So when I'm charging by induction, it means that I am not going to be touching it. I need to be making sure that my object is going to be grounded. And then I also need to make sure that there's no contact that's going to happen. So if this is my first piece that I'm going to happen, or that I'm going to have, I'm going to bring my positive rod. It's going to come close to, okay, well, maybe I should bring it looking like I'm bringing it closer. I'm going to bring it close to my sphere, but it's not touching. If you actually look at this, that's not touching. Okay, again, I have a bunch of the positives and negatives all flying over. Okay, because I brought it so close, I'm going to polarize, okay, the object. So all of the negatives are wanting to move here, and all the positives are wanting to get away. Okay, all the negatives are going to move to the one side. I'm going to ground my object. So I'm going to kind of ground it here, have my grounding piece this way. Once the object is grounded, again, only electrons can move, meaning that my electrons are going to be coming up this way. Okay, the electrons will move into my object. I will have my baguette, just seems to be growing here. Okay, I'm going to have my positively charged object here. Because I have my whole grounding object and the electrons are moving up, it is making this object more negative. There might be a couple positives here and there, but very few. Okay, and then I'm going to cut the grounding. So then I'm going to have a second object that's going to be negative. Okay, so what kind of charge will the neutral object have after charging? It's going to have a negative charge. Okay, then the second question says that I have an +8 charged object, and it charges a -2 charged object via conduction. So what is the charge of each object individually after the charging has occurred? Okay, so if you want to use it, draw a diagram to explain your process. So again, 2. Here I have my +8, so I can have 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to have a -2 charged object. Once they come into contact with each other, so once they physically touch, okay, again, when I have the things that are going to be moving through, they're going to share their two pieces, okay, and then when I separate them, they're going to have the exact same charges. Okay, so here, this is going to be plus, plus. Okay, both of these are going to have, because a positive and a negative are going to cancel each other out, they're both going to have positive 3 charge. Okay, just because it has that negative 2 charge doesn't necessarily mean that there's only those 2 pieces that are going to be there. There's all those other electrons that are floating around. Okay, but again, you have positive 8, and then you have minus 2. So I'm going to get that as a positive 6. And you have to divide that by the 2 charges to get positive, or by the 2 objects to get positive 3. Awesome. Okay, so what we're going to talk about today is going to be Coulomb's law, and then the talking of electric forces. So Coulomb is going to be the very first thing that we're going to introduce, and we're going to talk about this guy a lot. Okay, Coulomb is going to be used as a unit because he named it after himself. So Coulomb's law and electric forces. So we learned yesterday about the fundamental law of electric charges. So that's, we know that opposites are going to attract and then like charges are going to repel against each other. Okay, when we're talking about a Coulomb, okay, that's going to be much larger than a gravitational force. Okay, gravitational forces are Fg, so our mass times our gravity. Okay, when we're dealing with coulombs, it's going to be much bigger. However, as the farther the distance, okay, or the distance between the object as that increases, the actual Coulomb's law is going to decrease. Anytime that we're talking about Coulomb's law or how they found these pieces, we're going to pretend that it is in like a perfect state, kind of like a vacuum. Again, an isolated system, no other objects that are going to be acting with it. Okay, Coulomb's law, when we're talking, again, you haven't seen the formula yet, but we will get to it. It can be either positive or negative, meaning that this piece is going to be attracted or it's going to be repelled. So the universal symbol for a charge is going to be Q. So anytime on your formula sheet you see Q, it's going to be a charge. The unit of a charge is going to be a coulomb, which is just a capital C. So on your formula sheet, you will have this. It takes 6.2 times 10 to the 18 electrons to make up 1 coulomb. Okay, so this is going to be our elementary charge that we're going to break down to. If the charge E is called elementary, again, for both positive and negative, I'm going to have kind of this breakdown. Again, 6.2 times 10 to the negative 18 E, okay, is going to be 1 coulomb. Or again, if I want to figure out, well, what is going to be 1 E, I'm going to go 1 divided by 6.2 times 10 to the negative 18, and I'm going to get 1.6 times 10 to the negative 19. This is going to be my elementary charge for an electron. This is on your formula sheet, but we are going to be using it so much that you're going to memorize it by the end. Okay, so we do have this formula. I don't believe this one's on your formula sheet, actually. It's just one that it's good to know. We have Q, which is our charge, is equal to N, which is the number of electrons, times your elementary charge. Okay, the number of electrons, this is going to be an excess or it's going to be a deficit. Okay, so you need to know this formula here, Q is equal to N times E. We need to know this formula when it's asking for what is the excess or what is the deficit, and you're often solving for N. Okay, so in a question like this, so it says, what is the total charge on an object that has an excess of 10 electrons? So 10 more than its neutral object. So we're going to use this formula, Q is equal to N times E. Okay, well, I'm looking for what's the total charge, for that is Q. My N is going to be 10 times my elementary charge of 1.6 times 10 to the negative 19. Okay, in my calculator, I'm going to get the answer of 1.6 times 10 to the negative 18 coulombs. Okay, so that's the total charge of something that has 10 excess electrons. Okay, so 10 more. So this is kind of one of Coulomb's big experiments. Okay, so you might have seen something similar to it last year in Physics 20, but this was going to be kind of a force. It had a torsion balance. Okay, so in 1785, when I say Coulomb investigated that he wanted to know, well, what is the electric force between two charges? But then he thought, well, how am I going to do this? Because these charges are so small. How am I going to figure this out? Okay, well, he's like, okay, well, I can't take two charges, but I'm going to take two charged objects and put them on a torsion balance. What a torsion balance is, it's going to be this rod that has a string that's holding this two rod together. Okay, it is going to be spinning them around and around. Okay, the way that he's able to do this in this fancy big apparatus, and he's able to measure, okay, well, how far this little string moves from one side to the other, okay, and that's how he's going to figure out what the force is going to be as it's spinning. Okay, he does have different charges, so you see here he has a positive charge, two negative charges. Okay, well, how is this going to spin and change based off of where this positive charge is? Okay, the force between the small charged spheres causes this to rotate, and again, that's how we're going to be measuring it. Okay, well, how fast based on the charging is it going to be spinning? Okay, based off of this experiment, he was able to see that the force was proportionate to the product of the magnitudes of the charges. Okay, so that's just a fancy way of saying, well, the force was, again, our fancy little fish symbol, directly equal to, okay, Q1 times Q2 of the two pieces, multiplying them together. He also was able to discover that the force was inversely proportionate to the square of the distance between the spheres. Okay, so again, that's another way of saying, okay, well, the force was directly proportionate to 1 over inversely d squared. So if you find that two things are directly proportionate, okay, scientists often are like, hey, how can I do this? I'm going to stack them on top of each other. So I take this here, Coulomb's law of charges. So I have these two directly proportionate symbols that he figured out. Well, the force is directly changed. If I increase the magnitude of one charge by 2, the force is directly changed by 2. If I increase the distance by 2, it's inversely squared, directly proportionate at that point. He pushed these two together. So in your boxes on your sheet, the force is going to be directly proportionate to Q1, Q2, all over R squared. Again, when he was able to change these directly proportionate, same thing that when we learned with our gravitational constant last year in Physics 20, he was off by a certain amount. Okay, but it was the same amount every time. Okay, this became his Coulomb's constant. So we get our formula, F is equal to K times Q1, Q2, all divided by R squared. This is going to be the electric force. Okay, so Fe, and again, it is directional, between two charges. Okay, again, it is only going to be 2. Bring this up here. Okay, so Coulomb's constant, this number that he was off by each time was 8.99 times 10 to the 9. Okay, and then this is going to be his unit. Newtons times meters squared divided by Coulomb squared. If you derive this formula, when I have force, okay, I have my force, I times this by R squared, and then I divide it by my 2 Q's, which is Coulomb and Coulomb. That is how I'm going to get, well, force is measured in newtons, radius squared, well, radius is measured in meters squared, all divided by C times C, which is the same thing as C squared. Okay, so that's how I get my fancy Coulomb's constant. Oh, maybe I should leave that up there for you. F times radius squared, all divided by C times C. Okay. A couple things when we're dealing with, often because our charges are so very small, you need to familiarize yourself with one of the prefixes, which is This, it kind of looks like a U that has a really extra long nose in the front. This is micro, okay? So this is times 10 to the 6. If you do ever forget this, it is on your formula sheet as well, or times 10 to the negative 6, sorry. It is on your formula sheet and along with all of the other prefixes. So here, it says a comb has a -2 microcoulomb of a charge, and it's 0.15 meters to the left from a hair that has 3 microcoulombs of charge, a +3. What is the force the hair exerts on the comb? Okay, so again, we have to kind of think, okay, well, if I have a positively charged hair and a negatively charged comb, well, you need to know that we have opposites attracting, okay? So these are going to want to get towards each other. So we're looking for what is the force, the electric force. So Fe is equal to, okay, Q1, Q2 all over R squared. So Fe is going to be equal to my Coulomb's constant, which is 8.99 times 10 to the 9. My charge 1, okay, which is a -2 times 10 to the negative 6. And then my charge of Q2 is a +3 times 10 to the negative 6. Okay, direction does matter here, so we do need to be making sure that I have my charges are positive or negative because it's going to affect the direction. All divided by my radius, which is 0.15 meters, all squared. When I type this into my calculator, I'm going to get the answer of -2.397. I only want 2 significant digits, so my answer is -2.4 newtons. Okay, so we kind of need to be thinking of why does this answer give me a negative? Okay, well, the force is going to be going to the left. Okay, so what is the force the hair exerts on the comb? Okay, well, again, the hair has your positive charge. Okay, my comb is going to be my -2 charge. So I'm asking for the hair exerting on the comb. I drew these the wrong way. Oops. This way. My hair exerting on the comb. This is the force. Perfect. So I can have more than just the 2 charges. You can do this multiple times. So here I'm going to have 3 charges. You have a charge of 1.7 microcoulombs, that's 2.0 times 10 to the negative 2 meters away. And then a charge that's 2.5 microcoulombs, that's 3.5 times 10 to the negative 2 meters away. And then that's from a charge of -2 microcoulombs. So it says calculate the magnitude of the net electric force on the 1.7 microcoulomb charge. Okay, so I know that if the opposites are going to attract, I know that this negative here and this positive here are going to want to get to each other. Okay, but I also know that this positive and this positive are going to want to repel against each other. So that's why I have this repellent going this way and I have this positive kind of pushing this way. So again, we just need to make sure that we have our positives and negatives based off of what's happening. So I need to do my force between object 1 and 2, and then I need to do the force of object 1 and 3, because I want to know what is the net force on the 1.7, which is my object 1. So the force between object 1 and 2, again, K, Q1, Q2 over R squared. So I'm going to get 8.99 times 10 to the 9. 1.7 times 10 to the negative 6 is my charge of the 1. And then I get 2.5 times 10 to the negative 6 is my charge of the second. All divided by 0.02 squared. Okay, so my charge between 1 and 2, I'm going to get 95.5 newtons. Then for my charge between 1 and 3, I'm going to get K, Q1, Q3 divided by R squared. It's going to equal, again, 8.99 times 10 to the 9. If you want to store one of your pieces as the Coulomb's constant, I would encourage you to. Otherwise, it's going to be annoying to type that out. Times my 1.7 times 10 to the negative 6. And times my negative 2.0 times 10 to the negative 6. All divided by the radius of 0.035 squared. Okay, here I'm going to get a negative 24.95 newtons. Okay, so I have my two forces. I need to add them together for an F net. So I get positive 95.5 newtons, and then I'm going to add a negative 24.95 newtons to get my F net of 70.5, which I want two significant digits, which will give me 71. Did my adding go right there? 71 newtons. Okay. Positive. Awesome. Okay, so the last kind of thing before I let you go do some homework, when we're talking about Coulomb's law, this is only going to apply to point charges. So that's where we're saying that when I can actually pinpoint these charges and they're far enough apart and actually given those specific positions. If there's some charge particles that are around, because we always know that there's not just random things, or we know that there are just random particles floating around, that's what matter is made up of, they're not going to be significant. Okay, so we have detailed positions, we have specific spots that I'm going to say this and this one is this amount apart, and we need to figure out what these point charges are. Tomorrow you are going to be doing a lab. It's going to be Gizmo's lab. It's going to be Coulomb's force, and it's going to reinforce what we learned today, and then also going to touch base on maybe 2D that we're talking about after. So you do have your textbook assignment, page 530, 531, number 1, page 532, 533, number 1 and 2. If you do have questions, you can message me on Teams, but other than that, you're working on these textbook questions today, your lab tomorrow, and that's it. We'll move on to 2D Coulomb's law on Monday. Have a great long weekend, guys. Bye.